and welcome to another Algebra 1 video by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 2, Lesson 2, on solving using inverse operations to solve equations. Now, in the last lesson, we talked about what an equation was, right? Just a statement about the equality of two expressions. We also discussed what a solution to an equation was, which was any value of the variable that makes the statement of equality true, okay? But at the end of the day, right, we think of algebra as mostly about how do we find those solutions? How do we find x? How do we solve for it? And what we're going to be talking about today is undoubtedly, in my opinion, the most important equation solving technique of all, which is how we use inverse operations to get x all by itself and find that value that makes the equation true. So let's get right into it right now. All right, here we go. Let's do a familiar sort of problem from middle school. You've been seeing an equation like this since 7th grade, and let's do this as a warm-up. Let me just bring it to the top of the page. Here we go, exercise number 1. Consider the equation 5x plus 3 equals 23. Letter A, list the operations that have been done to the variable x on the left-hand side of the equation and the order in which they occurred. Okay. So let's talk about this a little bit. This takes us actually all the way back to Unit 1, Lesson 1, when we talked about variables and expressions, right? What we did back then is we took a look at an expression, just the expression 5 times x plus 3 on the left-hand side, and we identified what has been done to x and the order in which it's done. So I want you to forget about the equals 23, and I'd like you to pause the video for a moment and write down just for 5x plus 3 what operations have been done to x and the order in which they have occurred. Take a moment to do that. All right, well, we just have to remember our order of operations, right? In terms of that expression, 5x plus 3, the first thing that's happening to x is it's being multiplied by 5. And the second thing is that we then have 3 added as a result. So let's do that, right? Number 1, we're going to multiply by 5, and then we're going to add 3. Now, why is it so important that we can identify those operations? Well, that gets us into letter B. So let's take a look at that. Solve the equation by reversing what has been done to x. Verify that your value of x is a solution by showing that it makes the equation true. All right, so this is absolutely key. And before we get into this, I like to talk about what I call my shoes and socks analogy, right? I want you to think about your feet as being the variable x, right? In the morning, when you get up, right, you pull your socks on, you put your shoes on, maybe you lace them all up. At night, when you want to get your foot all on its own again, you unlace your shoes, take them off, and then you take off your socks. Notice that you literally do the opposite to your feet of what you did to put the shoes and socks on, and you do it in the opposite order, right? There's no way as you're like getting your foot all by itself that you're going to take your sock off first and then take your shoes off. That's just not going to happen. And that's exactly the case as well when we undo what has been done to x, right? So the idea here is to get x all by itself. We call that isolating the variable. What we're going to do is we're going to subtract 3, and then we're going to divide by 5. It's pretty much that simple. So let's do it. Right, here we go. We've got 5x plus 3 equals 23. So the first thing I'm going to do is undo the addition of 3 by subtracting 3 from both sides. Of course, 3 minus 3 is 0, and 23 minus 3 is 20. We can then divide by 5 on both sides. 5 divided by 5 is 1, but we typically don't write 1x, we just write x, and then 20 divided by 5 is 4. So we take off our shoes, we take off our socks, and we get our foot all by itself. In this case, we get the variable x all by itself. Now the problem also asked us to check to make sure that that value makes the original equation true. So I'm going to actually do that down here, because to actually check it, what I'm doing is I'm evaluating the expression on the left-hand side, and I'm seeing if it's equal to 23. It's basically that simple. So let's do that check real quick. I'm going to write it here. My check, right? I've got 5, x plus 3 is equal to 23, right? So now I'm going to put my variable in. I'm going to see if that's equal. Maybe I'll put a little question mark here, pretending I don't know whether it's equal or not. 5 times 4 is 20, plus 3 is equal to 23. Pretty sure that's true, but I'll finish it. 23 is equal to 23. Right? True. And therefore, x equals 4 must be a solution to this equation because it makes the statement of equality true. Okay? Now, the bigger point here is what we did. So let's kind of emphasize this, right? Absolutely important. The most important equation solving technique. If the variable you're solving for shows up only once in an equation, identify the operations that have been done to it and reverse them in the opposite order in which they occur. Take those shoes off, take those socks off, get the foot by itself, all right? This is unquestionably, in my mind, the most important equation solving technique. We're going to learn a lot of different ways to solve equations in this course. Many of the things, though, we do aren't really solving equations. They're just, manipulating things and writing equivalent algebraic expressions. At the end of the day, almost every single thing we do in order to finally solve an equation is going to boil down to this technique. So let's do some that are a little bit more complicated in exercise number 2. Find the value of x that solves each equation. In each case, first identify the operations that have occurred to x and reverse them. Show each step. All right, so normally we wouldn't just list these steps of what has been done to x, okay? We want to be able to just visualize them and think about them. But in these two, I'd like to do that. Let's do letter A together. We've got x minus 3 divided by 2 plus 7 equals 23. So let's list what has happened to x. According to order of operations, the first thing that happened was we subtract 3, right? The second thing that happens is that we divide by 2, and then the third thing that happens is that we add 7. Now, if you in any way struggle with trying to identify what is going on with x, think to yourself, if I gave you a value of x, if I said, hey, x is equal to 11, and I just said, tell me what the left-hand side of that expression or that equation is equal to, well, what would you do with the 11? You'd take the 11, you'd plug it in, you'd subtract 3, you'd get 8, you'd divide by 2, you would get 4, and you'd add it to 7, and you'd get 11. And then you would know that, well, it was not one of the solutions because it's not equal to 23. But that's how you could identify exactly the operations that are being done. Now what we want to do is reverse them, do their inverses in the opposite order. And we can already predict exactly what we're going to do. We're going to subtract 7, we're going to multiply by 2, and then we're going to add 3, right? So let's do that. Here we go. I'm going to bring that up here. Let me just write my equation down again. Here we go. Subtract 7 from both sides. Subtract 7. There it is. All right, that's equal to 0. So then we get x minus 3 divided by 2 is equal to 16. Give myself a little more space here. Now I'm going to multiply both sides by 2. Those cancel. I get x minus 3 is equal to 16 times 2. That's 32. And then I'm going to add 3 to both sides. And I'm going to get x equals 35. All right, that's it, right? It's that simple. We need to identify what's been done to the variable, and then we simply need to do the opposite of every one of those operations, right? The opposite of addition is subtraction, the opposite of subtraction is addition, and likewise for multiplication and division, and we need to do them in the opposite order. What I'd like you to do now is try to do exactly the same thing for letter B. I'd like you to first identify what happened to x, then I'd like you to reverse it in order to solve for x. Pause the video now and take a shot at this. All right, let's go through it. So the first thing I see is I'm going to just kind of like walk through them, then I'll write them down, is inside of the parentheses I have 1 being added to x. Then I'm multiplying that parentheses by 4, then I'm subtracting 2. All right, so let's write all those steps down. Here we go. Number 1, we're going to add 1. The second thing is we're going to multiply by 4. And the third thing we're going to do is subtract 2. So we should already be able to predict the 3 steps it's going to take to get x all by itself. We're going to add 2, we're going to divide by 4, and then we're going to subtract 1. That's it. So let's do it. Here we go. Let me pan up a little bit. Again, I'm going to write down my equation first. 4 times x plus 1 minus 2 equals negative 6. Move this a little bit out of the way. Here we go. Let's add 2 to both sides. That's going to give us 4 times x plus 1 is equal to negative 4. We're then going to divide both sides by 4. 4 divided by 4 is 1. That gives me x plus 1 is equal to negative 1. I can get rid of those parentheses since there's just a 1 multiplying. Now I'm going to subtract 1 from both sides. Be very careful here. I've got negative 1 minus 1, which is negative 2. All right, so it's easy enough, right? Identify what's been done to x, reverse it in the opposite order. Let's move on. Let's take a look at another thing to consider. Very often, there are multiple pathways to solving an equation, right? And all that means is that there's multiple correct ways to solve the equation, but ultimately, at the end of the day, you will use inverses to get x by itself. It just kind of depends on whether or not maybe you use some properties of equality or properties of real numbers in between. So let's take a look at an example of an equation that can be solved in 2 different ways. Let me bring exercise 3 up to the top of the board. Let's take a look. Solve the following equation 2 different ways. In A, reverse the order of operations that have been done to x. In B, apply the distributive property first. All right, so let's talk about this for a bit. Right here in letter A, it looks very, very similar to exercise number 2, letter B, the one that we just did, okay? And that's where I want you to begin. But a lot of students who look at this problem or who look at exercise 2A or 2B might think, I think I'd like to distribute first to get rid of those parentheses. In theory, there's nothing wrong with that, but we'll talk about that a little bit in letter B. What I'd like you to do now is solve letter A just reversing the operations. If you want, you can write down the operations or you can just think about them and then reverse them. Pause the video now though and use the technique we've been working on to solve the equation in letter A. All right, let's go for it. So what do I see? I see 4 being subtracted from x. I see multiplication by negative 2, and then I see addition by 8, right? So what do? I'm going to start by first subtracting 8 from both sides. Okay. When I do that, I get negative 2 times x minus 4. 2 minus 8, be careful, is negative 6. I'm now going to divide by the negative 2 to get rid of it. Negative 2 divided by negative 2 is 1. So I just get 1 times x minus 4, which is x minus 4. Negative 6 divided by negative 2, be careful, is positive 3. And finally, I'm going to add 4 to both sides, and I'm just going to get x equals 7. Lucky number 7. Okay, a lot of students are taught again and again that when they see a number sitting outside of a parentheses, they should use the distributive property to multiply through by that number. There's nothing wrong with that. When you use the distributive property, or the associative property, or the commutative property, what you're always doing is taking an expression that looks one way and rewriting it as an equivalent expression that looks like a different way that might make life a little bit easier for us. So let's go through letter B together to see how we can get that x equals 7 as a solution in a slightly different way. Let's take a look. So the first thing I'm going to do in letter B is I'm going to multiply through by that negative 2. So negative 2 times x is negative 2x, and negative 2 times negative 4 is positive 8. Be careful because we have that other positive 8 sitting there, and I don't want to sort of mix the two up. I can now simply combine those two like terms and get negative 2x plus 16 is equal to 2. And now I'd like to pause just for a minute and talk about this before we finish it up. All I've done at this point is use the distributive property and, technically speaking, the associative property of addition, which will allow me to add these two together before I add these two together. Right? All I've done is use those two properties to take this expression on the left-hand side and write it in a form that, for me, might be easier to deal with. Right? And now I can use inverses. Ultimately speaking, what's happening to x? I'm multiplying it by -2, and then I'm adding 16. So now, if we use inverses, I'm going to subtract 16 from both sides. I'll get -2x plus 0, which is just going to be -2x. Now I have 2 minus 16. Again, I should be careful. That's -14. I'll divide both sides by -2. -2 divided by -2 is 1, and -14 divided by -2 is +7. There's almost nothing more satisfying to me in math than when I solve an equation one way, I solve it another way, and I get exactly the same answer. And that's important because if I do everything mathematically correct in both methods and I come up with different answers, then something is deeply, deeply wrong with mathematics. All right, let's keep doing it. A few more problems on this. Of course, no one's favorite, we may end up having to use this technique when we translate word problems into equations. So let's just get a little bit of practice on that in order to end the lesson. Let's take a look at exercise number 4. Set up equations that translate the following verbal phrases into mathematics and then solve the equations using inverse operations. Letter A. 10 less than 5 times a number results in 35. What is the number? Carefully set up an equation, solve it, and check your answer for reasonableness. We'll talk about that in a little bit. Watch out, subtraction is involved. All right, so we got some practice a few lessons back on translating English phrases into mathematical expressions. Not equations, but expressions. And you can see that kind of right away in here where we see 10 less than 5 times a number. 10 less than 5 times a number. So how do we translate that into a phrase or into a mathematical expression? Well, let's say that the number is n. 5 times that number would be 5n. And 10 less than that would be 5n minus 10. Now you have to be very, very careful here, right? Because it's easy, given that the word 10 comes first, it would be very easy to assume that it's 10 minus 5n. But that would be 5n less than 10. Not 10 less than 5 times a number. All right, so how do we get the equation? Well, 10 less than 5 times a number, which is this, results in 35. You have to kind of see the equal sign there. Results is the equal sign. Is equal to, results in, right? Those things are all giving you, right, that equals 35. Okay. So I've got my equation, and solving it now using inverses is relatively easy. Pause the video now and go ahead and solve this equation. All right, well, what's happened to the variable? We've multiplied it by 5, and then we've subtracted 10. So when we undo that, we're going to add 10 and then divide by 5. Here we go. Add 10 to both sides. We get 5n is equal to 45. Divide both sides by 5. 5 divided by 5 is 1. 45 divided by 5 is 9. Now, I said check for reasonableness. Look, if I've set up the wrong equation, but I've solved it correctly, then if I take the 9 and I plug it into this equation that I've set up wrong, I haven't, this is correct, but if I had set it up wrong, let's say I did 10 minus 5n, well then what I would find out is that, yeah, sure, it works. But I actually like to sort of think about this in the context of the problem. 10 less than 5 times a number results in 35. So if I want to think about this, I might say, well, all right, like what is 10 less than 5 times this number? Well, 5 times 9 is 45, and 10 less than that is 35. So yeah, right, it's correct, right? It's reasonable. So let's take a look at our last problem. Letter B. When 3 times the sum of a number and 7 is increased by 10, the result is 4. What is the number? Carefully set up an equation and solve it. check for reasonableness. All right, I'd like you to pause the video now, try to set up this equation. It's going to be a little bit more complicated than the last one. Try to solve it and check for reasonableness, and then we'll go through it all. All right, well, let's take a look at that mathematical expression. 3 times the sum of a number and 7 is increased by 10. Well, again, let's go with n as our number, right? We've got 3 times the sum of that number and 7, okay? So the sum of the number and 7, that's easy enough. That's n plus 7. I have to be careful now, right? That's its sum, and this is 3 times that sum. So that is 3 times the sum of a number and 7, right there. That is then increased by 10, and the result is 4. Let's talk about this for a moment, and then we'll go ahead and solve it. So, you know, one of the real issues here that a lot of students will do is they'll just simply have 3n plus 7, right? Which is actually 3 times a number increased by 7, right? This is the sum of a number and 7 that's then been multiplied by 3. And now we can solve it using inverses, right? We've got n being added, 7 being added to n, then being multiplied by 3, and then having 10 added to it. We're going to undo that by subtracting the 10, dividing by the 3, subtracting the 7, and we'll have n all by itself. Let's do it. Step by step. Here we go. Subtract 10 from both sides. We'll get 3 times n plus 7 is equal to negative 6. Divide by 3 on both sides. 3 divided by 3 is 1. So we get 1n plus 7. Then we get negative 6 divided by 3, which is negative 2. Finally, we'll subtract 7 from both sides. And negative 2 minus 7 is negative 9. I love the 9s in this problem, apparently. Love it. Now, it is a little bit harder to think about how reasonable this answer is because it's negative, but we can still do it, right? We've got the sum of a number and 7. Well, negative 9 plus 7 is negative 2. If I then multiply that by 3 negative 2's is negative 6. And if I take negative 6 and I increase it by 10, I get up to 4, right? So it's the correct answer. And notice again, I was kind of working that out from the verbal description rather than just substituting it back into this equation. All right, let's wrap this lesson up. Okay, so today we looked at how you use inverse operations in order to solve equations. And again, I know I talked about it a lot at the beginning, but I just cannot emphasize how important this particular topic is. We will solve almost every equation in one way or another by using this technique. Maybe the only way that we won't use this technique is when we use our graphing calculators and technology in order to approximately solve equations using graphical methods. But besides that, one way or another, you're going to be using inverses in the opposite order in which they occurred to get your variable all by itself and solve for that value of x. All right, well, we'll certainly see this a lot more in future lessons. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.